of the beginning. It's my pleasure to introduce Tiziana Di Matteo today. Tiziana is a professor in the physics department and the director of the Max Williams Center for Cosmology at Carnegie Mellon University. She received her PhD in 1998 at Cambridge University, and she was a Chandra Einstein Fellow at Harvard and a junior faculty member at the Max Planck Institute for Astrophysics in Germany. And Di Matteo is a theorist with expertise in the art of cosmological simulations of galaxy formation, with special emphasis on modeling massive black holes across cosmic history. Now, let me tell you in 1 minute how we met. Of course, I've known Tiziana for many years by fame.
I have a very long talk. You don't want to use
No, 1 minute. But then we were in Aspen, and I was very curious about, because her name is obviously Italian, and I was looking through her CV and looking for where she was, originally from, and I couldn't find anything because she did the graduate and undergraduate student in UK. So the first words that we told to each other was, "Are you Italian?" And she said, "Sì."
Thank you so much, Fabio. It's an absolute pleasure to be here. I actually hadn't visited the VHI yet, so it's a real privilege to spend a day here, particularly in the midst of our busy semester time. This is like playtime that you get a few days here and there. Okay, so I want to tell you a little bit about massive black holes and what we can attempt to learn from these cosmological simulations. I'll talk about this. I'll add these two little guys sometimes, just when I use some schematic drawings. They're going to be black holes. They're not black, they're not holes, but neither are the real ones. They have no hair, so I guess maybe they could work. Anyway, so just moving on. Let me just start saying, okay, Fabio did a good job introducing who I am. And here is, I'm talking to you, of course, on behalf of this team of people. Lots of them are here. There's Ye Yang. She was a graduate student at Carnegie Mellon. Now she's here. Hopefully you all know her. Other graduate student who's about to graduate, Nian Chen, and who's contributed tremendously to all of the things that I'm telling you today, and as well as many of the other graduate and undergraduate students and other faculty, other people that are associated with the VHI I had the pleasure to work with, including Fabio himself, and Priya and Angelo, and of course even your amazing undergraduate Emma, who's here, and the first time I meet her. Hi Emma, it's lovely to meet you too. So as usual, a lot of these projects are a big team effort. This is not a humongous team, nothing compared to your team here, but it's definitely all the credit goes to all these people, which I'm going to continuously forget to acknowledge enough. So I wanted to do it right off the bat. So I was told that this talk should be addressed to a very broad audience. So please interrupt me if I'm failing to explain something that, or I'm using some acronym or something that you don't understand. It's a really nice, crowded, small room. I like that a lot. So, but what I want to talk to you about is massive black holes. I don't have to say this to you. I hear that there are key players in our cosmic history. We've certainly discovered more about black holes in the last decade than in any of the previous ones, and we continuously do so. The beautiful discovery, at least for me, I'm sure for you, also comes from you guys here. We have imaged black holes. We know black holes in the universe today to the point of imaging their event horizon, but we know that the black holes that you've imaged here are inside of galaxies, right? So in the modern universe today, this is just a very schematic timeline. Here is the universe today. Black holes are in every galaxy, pretty much. They manifest themselves in different way in the local universe. But modern galaxies, whether it's an elliptical, whether it's a spiral galaxy like our Milky Way, or an elliptical like the host of M87, or even perhaps dwarf galaxies themselves, the much smaller units that are we know even those likely contain black holes, but for sure the bigger galaxies, any kind of galaxy contain black holes. We probe the local universe in all sorts of ways. We have parts of timing array that now have discovered also a background due to the gravitational wave emission from these massive black holes. But black holes were already there, cosmic noon, right? When the universe is roughly half the current age. That's how, well, around the epoch that we've discovered the presence of black holes indirectly through quasars, right? Quasars are massive black holes that accrete quite copiously, much more than the local black holes. So they could be seen out to very large distances. Around cosmic noon, quasars are extremely abundant. Black holes are accreting very large amount of gas. So there's we know about this quasar population, this massive black hole population at cosmic noon very well, again through a variety of multi-wavelength observations that we've been doing. And they've been known, quasars have been known for maybe 50, 60 years or more. We've also discovered over the last decade, or maybe a bit more, but certainly consolidated over the last 5 years or so, that there's very massive quasars already when the universe is only 1 billion years old, right? So these are what we refer to often as the first quasars. They were discovered serendipitously in these very large surveys. They're extremely rare, but they're there. There's black holes as big as black holes are in M87 in the universe today, but they are already formed when the universe is 1 billion years old. So when the very first galaxies are forming around this epoch where we haven't quite even reached 1 billion years old universe. So they're there. Most recently with JWST, we are perhaps seeing a whole population of other black holes at this early epoch that maybe they're not quite the tip of the iceberg, not quite as extreme as the first quasars, but perhaps they're even more interesting in some ways that they're there. So they are absolutely key players in this cosmic history, and we'd like to understand how they form, right? If these quasars and this JWST, perhaps detection of these little red dots are already assembled at this time, it tells us automatically that black holes must have formed even earlier. So we refer to them as the seed black hole population, those black holes that in fact then grow and make up the rest of this population. And by the fact that we're already seeing black holes really massive at the universe that is very young, this must have formed at the sites of when the very first stars formed, right? At when the universe is around 100 million years old or so, right? And so all of this history, right, it's directly probed by a wealth of beautiful observations and so on. These are not observed. We don't know yet. We cannot see them at the time of formation. We have no access to them. And even JWST probably won't see them directly. And we'll go back to this, right? So we know that we made all this beautiful discovery, yet we do not know how this population of massive black holes that pervades our cosmic history actually forms. We don't know the origin of this population. So I'll touch back onto that. And
so do the first galaxies have supermassive black holes?
We don't know. Yes, that's what we don't know. Okay, so re-emphasizing that, right? So we have these massive black holes everywhere, but we have been stuck on this problem. Do the very first galaxies form a black hole? How big is it? What is it like? And we have some ideas, of course, because theory will. Okay, so what is the issue? Maybe you say, okay, but why can we see from the massive black holes, again, my little black hole guys here, right? These black holes, do they actually have any information about how they started? And the answer is obviously no, right? We can measure a mass and that's pretty much it. But they will have erased their history, their origin, the way they were actually seeds. Very, very schematically, very briefly, how do we think these massive black holes have built up to these very large masses, million to billion solar masses or so? They could have done it in a number of ways, all of which is complex and messy and cannot let us trace back their origin. Again, schematically, how do they get their mass? Maybe they started from little black holes, right? And many of them emerge, and then there's a little bit of gas, accretion of gas onto these little black holes that have already emerged, and they end up in a massive black hole. Perhaps they've actually started off for something a little bit bigger, and then gas has grown them again. Perhaps they started from just one single tiny black hole, which has a ton of accretion. All of these are viable. And perhaps a mixture of this, and any kind of complex mixture, chaotic configuration that is, across these three things. And bottom line, they just had this complex history that we're not going to see the seed when we actually look at massive black holes. We're not going to be able to deduce it directly from the massive black hole population. We just don't have a chance to do that. And I'm going to go back to that. So back to the cosmic history now. So I said what massive black holes are, why they're so interesting, they pervade our cosmic history. And how do we study the emergence of structures and cosmic history and longer cosmic mystery, black holes and galaxies? And I kind of edited this quote. I don't know if you know this quote originally is the unreasonable effectiveness of mathematics in the natural science. And I call it, what we use is the fact that there's an unreasonable effectiveness of physics-based models, right? So that's what our simulations, what I said, I was going to tell you about cosmological simulations, and this is what they are. This is quite an old movie, but it's very illustrative as an example, right? So we have simulations that simulate the emergence of structure in the universe, right? This is from the illustrious collaboration. So we see this filaments, this is matter, this is in particularly the matter in this image, and the colors are gonna change. So we see the universe emerging from the fluctuation of the cosmic microwave background. This gives us an idea how it rotates. Now suddenly you see explosion, the gas that is in galaxies actually being moved out. This is probably an effect of star formation and supernova feedback. And AGN feedback itself, the quasars in the central galaxy itself. So we see this lump of matter, these are galaxies, right? And inside of galaxies, there are already stars and black holes, and this give rise to this very complex picture that I'm going to be using over and over again, okay? But this is sort of taking us in a little quick movie across the history of the universe. We have this beautiful physics-based models. We arm ourselves of all the physical laws that we think are relevant to making a universe, right? We have an initial condition, the CMB, that tells us what initial matter fluctuations are. We try and reconstruct this history. We reconstruct it, and I haven't gone through all the colors of this and what every single piece of this is. We reconstruct it by actually building all these basic structures, the galaxies, the large clusters, the galaxy, and actually also the black holes that go into this history. These are, from my quote, it's quite fascinating. They're quite, indeed, quite effective, quite powerful. They are really become the primary avenue for us to understand galaxy formation and black hole formation across from the very large cosmological scales, billions of light years to like almost light years now. So they have this huge dynamic range. They're very effective because once we put in as much of the physical laws that we can into one of these models, right, and we play this universe on our computers, we have really a way of issuing predictions, right, for what things should be. Sometimes they even go beyond the current state of the data, but at least also issue predictions that we can compare and validate against the universe that we see. So I don't know how you would not want to work on this. It's really fun. But okay, so this is where we are. But yeah, so these are the tools that I'm going to be telling you about a lot today, this large cosmological volume. This is a very nice picture that Yang has put together. You'll see some of this. So this is just a slice, right? So that movie was kind of rotating and would show the full 3D distribution. We usually plot it like that in 2D. So we project so we see the large scale structure of the universe. There's different colors. They represent sort of how we see the density in the dark matter, the temperatures and so on. So this is just different stripes that are colored by a different physical property of the simulation, but not to worry too much about it. But often we're showing sort of insets like this in the simulations. What we're showing really is imagine you have this picture on your phone and you're literally zooming in, right? And you see more and more detail. So all of these structures, we cannot show it in this image but the simulations have a huge dynamic range that actually resolve processes across all these different scales. As I said, sort of billion of light years to bigger superclusters, to very large groups of galaxies, to single galaxies and black holes moving around galaxies, and all the way to the very inner structure of these galaxies. These are scales that are directly resolved within the same simulation. Okay. So if this is our major tool that we want to, where we study structure formation, galaxy formation, then this is the tool that we are going to try and use, right? And see if we can gain some clues also how massive black hole formation is connected to this galaxy formation and to large scale structure of the universe.
How do you map the time scales of the simulation to real cosmological time scales? That seems, do you map that? How do you know how long some process takes?
So you actually have, you're just doing it on a computer. So you're putting this 14 billion years of evolution onto, a time step that has to be, big enough that you can do it in a few months or in a supercomputer. So the time step is simply given by the dynamics that you're resolving. So you're putting in certain physical laws, right? So you're sort of looking at, how fast the gas cools, what is that time scales and at the resolution that you have. So the time scale is still, every time step is going to be 1 million year of the universe at best, right? Because that's the level of physics that you resolve. So a current condition, a gravitational time step, it's roughly of that order. So it's kind of related to how good your resolution can be. But I'll show you also something better to just picture in your mind, really. This is absolutely the frontier, state of the art. So if you can't imagine how we can couple black holes and their structure into this very large scale structure of the universe, this is matter, very large scale structure. Just watch this and enjoy this absolutely awesome unit that as the group of Phil Hopkins has just put out. So this is, if you're not familiar with these units, these are kiloparsec. 1 kiloparsec is roughly 3,000 light years, right, across. So this is a very, very large scale structure, like in the picture I showed before, right? Where is the black hole and what is it doing? We are going to zoom in, zoom in, zoom in. Watch this as well. You're going to zoom in into this. This is the matter distribution around a very large galaxy. But then we keep going in and going in. And we're now at parsec distances, tens, and further one, and sub-parsec distances. We're getting close to like things that are, and here's your black hole with its accretion disk. This is the gas, right? So this is an hyper refinement and hyper super resolved region. We are almost like solar system size at the end. So this is what it really, really means that we are trying to do, and Phil has done it for the first time at this level. This is just one galaxy. It's not a full universe of galaxy where he's been able to do this, right? This inner structure, this structure evolves for only a few days, talking of time scale. So it doesn't evolve over the full history of the universe, right? Just because of the challenge that he's meeting by doing this absolutely crazy dynamic range. What is it? Over 1 million or something scale.
Tiziana,
Yeah.
does this simulation actually resolve the MRI?
They do talk about this, close to it, very close to it.
Okay.
They even find something else that is slightly different to MRI, and they think it's working quite well. And another way in which they think we may be able to transport angular momentum that they see, but it has MHD, it has everything, yeah. It doesn't have GR though, so it's not quite on the way. Okay, so this is the absolute frontier, fresh as a week or so ago, although Phil had told me about his work and his team. There's definitely a really good team.
Simulation doesn't have GR.
No, it doesn't have GR, yeah, not yet. maybe put it in. So this is a larger scale where, you know, the black hole is the GR effect. But you're right, yeah, it'd be very interesting to add to it, yeah. So this is the accretion disk that forms around a black hole, but we're still at, you know, sort of the outskirts, far from the horizon. Sorry, no, we want to move on. So this is not what we're able to do in this very large cosmological volume that I'm going to be talking about. But let me tell you a little bit more. If you already work on this, you already know this. If you don't, you probably don't care about details so much. I'm going to be talking about one particular simulations where we have a very large dynamic range. It's not going to be that dynamic range you just saw. We cannot simply do that at all in this very large volume. So we have to make some compromises. So now I'm going to talk a lot about simulations which have very large sizable volumes, right? So now we're going not just one galaxies, but populations of galaxies, billion of light years across. They're still the highest resolution simulations that we can do right now with this level of physics. Obviously, when we see this evolution, the first movie I show, there's gravity there, obviously, bringing matter, you know, to where there's already matter, building galaxies and so on. There's also, I briefly touched on, there's obviously gas, there's a baryonic part of the universe, gas that cools, makes stars, gas that goes into feeding a black hole, but this physics is done in a coarse representation in the simulations, which we call subgrid modeling, which is the standard way we do this in the simulations. These are enormous calculations, right? And this is one that we've been running for a while. Ying here has been doing the great majority of the lift to get this together and running it. And it has black holes that are getting seeded in the simulation, and I'll talk about it. It also has a way in which we capture how black holes move into galaxies, dynamical friction for the black holes a little bit better, and a whole suite of physics that tries to capture to the best that we can at the kind of resolution that we can what we need to make sort of realistic galaxy population in this universe, as well as black hole populations within them. So just again, another one of these 2D projections, just again, these are what we already have in the simulations, right? So every little point, maybe you can't see it here, is a black hole that is embedded in this very large scale structure, right, of the universe. This is the matter distribution at large scales. But then as we go and zoom in into these little things, we find all our little black holes. There's sometimes black holes in galaxies, right? Sometimes there's a merger with two black holes. They are going to come together as the galaxy come together. I'll show you a little movie of that. But we have this large population of galaxy and black holes, not to the exquisite resolution, but we resolve things pretty decently. So just to give you a sense of what kind of scales are we at with these very large simulations, right? So again, this is this way of showing the different scales that we have self-consistently in the simulation, right? So this is a very large group. Then from the large group, right inside, there's a galaxy. A galaxy, I'll show you what these little crosses are, or these little black holes. Right in the center of another galaxy here, there's another two black holes that are indicated by crosses. I will use these crosses, right? It's hard to show black holes. And this is sort of where the simulation kind of gets to has a resolution that is just below a kiloparsecs, right? Around 3,000 light years and so on. And this is basically running on the biggest computers right now with as much physics as you can. That's where you can get to when you also want to keep track of the full large volumes. There's other scales that you'd like to resolve, right? So we like to think about these black holes coming into galaxies and eventually perhaps merging. So they're going to move in, they're going to experience dynamical friction to a point. And then at some point we are going to lose the resolution in the numerical calculations to fully follow them, and they're going to enter into the regime where there's other things that, like stars, that contribute to Roscon scattering and eventually gravitational wave, and much smaller scales, right, that we don't follow completely. So we use these tools, but once the black holes are already inside of galaxies in a really small region of galaxies, and we don't have the capability of doing that amazing resolution that you could do on only one particular galaxy, but we want to keep track of the full population, what we can do is to resimulate that galaxy with its own black holes that is matched to the large conditions, right? This is just an example, and gain a lot more of these other scales that we are missing. So in this case, it's sort of, you kind of extract something from the large scale simulation, you extract it to that point, and then resimulate it at much higher resolution by feeding all the sort of outer boundary conditions from the very large simulation. So this is just an example that gives me a chance. So this is a resimulation, but now we've gone to much, much higher resolution for one particular system that was already in that asteroid simulation. And we are zooming in scales and seeing, you know, in this case, there were two galaxies, there was a black hole merger. And, but we're going much, much deeper at resolving these processes once black holes are all the way inside of galaxy. This is another example where we have multiple black holes and multiple galaxies coming together. I'll show you more of this in a second. And again, we are sort of feeding all the information from the larger scales and then resimulating at much higher resolution so that we can follow the dynamics of the black holes, as well as continue to resolve other processes in the galaxy, star formation, and so on. So you saw these things moving along. Just to focus for a second, what kind of information, what kind of things are we doing with the black holes? This is the luminosity of a black hole. So we actually follow the accretion of matter. This is done by some subgrid representation of what matter should be doing close to the black hole, close to the accretion disk. So gas is coming in as being fed into the black hole, giving rise to volumetric luminosity, right? So it's very variable. You see them going up and down as the black holes move. These are both of the black holes that were in that simulation that are moving into the center. They're both accreting gas at some rate, and as they're moving in, what is plotted here is their distance as a function of time. These are million years, right? So the black holes in this case were going through a merger, they're coming in and eventually in spiraling and moving all the way into the smallest region that we can resolve. Okay, so bottom line, we can start from a very large universe and then take all these galaxies that have, you know, interesting black hole and resimulate them so that we gain much deeper understanding of what's happening to their accretion, their gas around them, and what's happening to them as to their dynamics as they move closer and closer to the center. Yes.
I would have thought you'd get big spikes in the luminosity when they come close together.
Yeah, but they don't come close enough because of resolution limits. Absolutely, yes. So yeah, we're still not quite at that point. But we can go further. You know, we can do even resimulation of that region, and actually, that's something that with my group we're trying to do. So okay, so let's move on. So these are the tools for today, and hopefully I can change slide. Okay, so now I told you a little bit about the tools. The dream tool, that amazing simulation plus GR, that's our dream, right? But we can make a compromise, and I'm going to show you what can we learn, what kind of clues, what kind of hints can we learn from this sort of nested resimulation, but keeping the information of this universe evolving with a black hole in large populations. So I kind of touch on this problem, the seed black holes. So I want to go back to it a little bit. So take it as a little bit of a somewhat deep dive into one of the aspects in this cosmic structure formation and black hole formation that we can sort of go into the simulation and learn something about. So the seed black holes, we don't see them, right? So this is zooming in into a little bit of what we talked about in this cosmic history, right? So these are the things that we want to know. We don't know how black holes form, but if we get some handle on these seed black holes, we may be able to learn something. So we haven't seen them, but that hasn't stopped people trying to imagine how they're formed, right? So what are the dominant ways in which we form these seed black holes? These are ideas, right? They also here are schematically represented. This is a huge, large body of work. The simulations I'm showing you don't follow these processes directly, but they follow these ideas, right? And particularly the idea that it's likely that the seed black hole population, as I'm showing here, forms through this process, this model that we call direct collapse model. So this is sort of the leading theory for how these objects are formed. And what we have is that early in the universe, we have a gas cloud, that gas cloud, it becomes genes unstable. And if it does not fragment and other conditions come, it can actually collapse directly into a black hole and form black holes that are up to 10,000 or so the mass of the sun or more. There are lots of conditions that have to be met in order for this gas to not form directly stars, to do some, and come into this black hole. But this is the leading theory, and this is sort of the idea that we capture in the simulation as well, by simply saying, okay, when we meet some condition that the first gas, we start some gas cooling in the simulation, it's low metallicity, so we have that information, then we can put in one of these black holes, although we don't directly form it. Other ideas is that would make these seed black holes much lighter. They would be coming from more like the standard black holes in our galaxy, that a black hole, like a solar mass black hole, is at the end of a massive stars, right? It forms as a result of stellar evolution. These would form also as a result of stellar evolution, a much more normal process, but are the very first stars. And the very first stars could be more massive than the typical stars that we have today. And they could end up with black holes at the end of the formation that are closer to 100 or so solar masses, but there's a lot of debate. The truth is probably we're in between any of these may work. And we're looking for evidence of which one is perhaps more predominant, and can we get some clues? Remember, this will not be directly observable in the early universe, any of this process, not with JWST, not in the near future.
Wasn't this supposed to be easier for stars to collapse into black holes early in the universe? Or is it supposed to be harder? Because the universe was smaller, there might be more pressure, essentially.
I mean, everything is basically local, right? At that point, you decouple. At that point in that object, you're decoupled from the expansion. But yeah, so it's pretty much the same idea. It's just that we think that the first stars will form differently. The universe is pristine, right? The first star forms in a completely non-metal enriched environment. So the stars are probably, and that's something how these first stars, we call them population 3 stars, form, and how these lead to black hole formation. It may be faster, likely to make it, right? Because the stars are likely to be very massive, but there's a lot of debate exactly what is the mass function of the stars and how they form. So it depends a little bit on that.
I know that, the question you asked is a very good one, which is, given that galaxies seem to have black holes, how could they form and so on?
Right.
But could a galaxy form without a black hole at its center? Is it dynamically? Are they required dynamically?
No. Yeah, it's just that we have them and they're
No,
everywhere.
I
And we
get
can't
that.
avoid that question, but they could have. So I think before we knew about you couldn't make a universe possibly without black holes in the central galaxies.
So they're not essential for the formations.
Of the galaxy. Let's say we don't know. Maybe they are. Maybe the black hole forms first. The question, we really don't know how it forms, and that question becomes a bit fuzzy. But possibly no, it wouldn't be clear to that requirement.
One example of a galaxy where there is no black hole in the center.
Do you know any galaxy with
Not detected.
Not detected?
Yeah.
That's the problem, right? So as people do the hard job, not the simulation, but the actual observation, that's when they do the hard work, right? But they try and detect black hole, and they have limits on these detections, right? But they cannot exclude the presence of a black hole almost in anything that they pursued. And I'm going to go into this a little bit, show you some observations. Yeah. So if you have firm evidence, right? So we can't see these black holes forming. So how can we see them? If black holes are formed really, really early on in this first galaxies, and this could be actually, we expect then that there could be relics of these today. So suppose these black holes are formed, when there's a bunch of mass emerging that goes on. In a massive galaxy today, we could have relics of these black holes that were formed there, because these galaxies were free, but their black hole didn't make it all the way to the center, they're left, right? So if there's a lot of merging, today we have a big galaxy because this big galaxy has formed from all this merging, but likely also a bunch of black holes sticking around. That could be the remnant, the relics of this early population. We also have places in the universe that are very isolated. So you could have formed a black hole in a little dwarf galaxy early on, and this could have evolved pretty much in isolation, not doing all this messy merging. And perhaps if we go and look locally in this dwarf galaxy, we may find some of these relics. So a key prediction of the seed black hole population is that we should have some of these relics today. And perhaps that's our best bet to finding or constraining some of this intermediate black hole mass population. Of course, because this is a pretty straightforward idea, the hard part comes with observation, and there's been a tremendous amount of work. This kind of observation has really been building up momentum in trying to look for this off-nuclear black hole sources, right? Black holes in the middle, we know about those, but in some cases there are very bright sources. This is an edge-on galaxy in which we have a source that is producing a lot of X-ray. HLX means hyperluminous X-ray sources. Is actually very faint, but of course it's hyperluminous for being a very small black hole. So this very annoying acronyms, right, for people not in the field. But the point is that this could be accretion, a little bit of accretion onto something that is an intermediate mass black hole, one of these heavy seeds, that is in offset from the galaxy. This is a really cool object that flares up and does all sorts of fun things anyway. But yeah, these are the kind of observation, the kind of hints we're getting from observations. Obviously, getting a mass, it's hard, but you know, these sources are there and just not one galaxy. Sorry, this is kind of low res. There's definitely been surveys with large surveys that have looked at this hyperluminous X-ray sources and found some population of these X-ray sources in various ways. There's a lot of momentum that has been built up. We can also look for dynamical evidence of these objects in nuclear star clusters. So there could be, if there is an intermediate mass black holes, these neutral star clusters, by studying their dynamics, and this is again really exciting work done by a variety of teams, we can infer whether there is an intermediate mass black hole in these very dense stellar clusters, and there are indications that there are. This is indirect evidence, of course. We have tidal disruption events. So a star could come close to one of these black holes and be ripped apart. And in this case, there is a detection off in a little galaxy here that could be the putative host of an intermediate mass black hole where one of these tidal disruption event took place. And there's just this I'm not making justice to this field, but there's a lot of momentum in trying to do this. So this is extremely hard, and it's very hard in any of these with any of these tools to come up with a mass for these black holes. But the limits place them around these objects that are these intermediate mass black holes, these heavy seeds. So now moving on to what I'm going to tell you about, the simulations. Do the simulations have these intermediate mass black holes, and have they come into galaxies and they're there? Yes. Okay. So these are a bunch of galaxies that we have in our simulations. They're shown. So this is the stellar component in the background. Every single red cross in here, it's a black hole, and it's a black hole that is that was left in these galaxies through this process of merging. So we're seeing a snapshot at a given time, but these galaxies have gone through many mergers that have gone through many with little galaxies, right? And these mergers are left behind this large population of intermediate mass black holes. Those came from having seeded them in the simulation early on, and with subsequent mergers have kind of built up these large populations in the simulation. So let me show you more, like a little piece of the simulation where we see what they're doing. Okay, so this is across the little time sequence, right? So again, every little cross in here with their own track is a black hole. There's a massive black hole in the center. There's black holes in satellite galaxies, like our Milky Way has satellites going around it. It's going to play again. So there's black holes in satellites. The black holes, they are sort of wandering around because they came in through a satellite, but the satellite galaxies got tidally disrupted, and only the black hole is left and is sort of moving around and doing its own things. Okay, so this is our nice, fun, messy universe full of black holes, right? So this is just one example, and this is what we see quite a lot in the simulations, right? So we have lots of black holes wandering in the halos of galaxies, in the outskirts. Dynamical friction is not so effective, right? It doesn't let them, they're light things, right? They move, they orbit, but sometimes they go by, the galaxy gets stripped, but they stick around. And with time, we're roughly half the age of the universe now. With time, this large galaxy would have accumulated a lot of these wandering black holes. Some of them are still stuck to their own little galaxy. They are satellites, right? So lots of these are also intermediate mass black holes. And there's a lot of messy stuff. I'm going to zoom in a bit. Some are orbiting the center. There's a supermassive black holes that are in the center, and some of these are going around there too.
In your simulations, do you always make black holes in the center of galaxies? And how do you like choose the mass of those black holes themselves?
Yes, so it comes from that direct collapse model. So the mass of the black holes that we make is between 10 to the 4 to 10 to the 6. I had that little schematic plot I didn't go through. So we're saying they're likely to be in I have this sort of power law distribution, and we sort of randomly distribute them very early on, anytime that a new galaxy is forming, so in the early universe, and that is starting to have some cooling gas that sort of represents coarsely what we think, how we think this forms. So most of them form early on when the very first galaxies form, which is a little bit resolution dependent, but they form very early on in the smallest structures, the smallest galaxies that you can resolve. And they can have sort of different masses across between 10 to the 4 to 10 to the 6. So they're within the realm of this intermediate mass black hole seeds that we put in.
If you don't have GR, do you just say that something is a black hole if it's too massive or something?
Yeah, I mean, here we're just saying it's a black hole. This is my particle that I just call it black hole. Yeah, so we don't have, yeah. But what do we see for these black holes now in the red crosses? We're seeing the black holes that are accreting enough that they may actually show up as these hyperluminous X-ray sources that have a flux in X-ray that is about 10 to the 42, 10 to the 43. There's a lot of work that was done here, but immediately you see these red crosses now are way fewer than the crosses in the previous image. The previous image didn't care about their observability, right? They're just there, they're just doing their own thing. Here is when we remember that our black holes have some kind of accretion onto them that follows the gas around them and so on. But when we look at the simulations, right, and this is work also done with Emma and Fabio, we find that only about 1 in 10 or even less will be detectable as an ultraluminous X-ray source. But that's good, because if we want to say that these tell us something about the seed black holes, we don't want them to grow. So we want them to see that, and some of them to know that they're there. But if they've accreted a lot, they've erased their seed black hole mass, right? And they would have if we find them as strong accretors, we again are in this problem that we cannot say what their initial seed mass could have been. Right, so this is just a little inset. We're looking at one particular object also to say maybe sometimes, so these black holes are moving, right? Like you saw in the previous movie, they're moving in, and some of the high states of accretion, this is the accretion rate that we also show, right? This looks like very small flares, but they're over a large time scales, right? They occur when the black hole is going toward the center of the galaxy when there's more gas. So it's not like they're just on all the time, they're on when they actually move closer to enough gas. So, and then they may move out again and so on. So this is kind of interesting as well, that there's a duty cycle to this that depends a little bit how these black holes are actually orbiting around the galaxies and where they are. Okay, so they may be, we may see some of this population, but they'd be the accreting population. There definitely could be some of these hyperluminous X-ray sources, but it'd be hard to find them. And that's good and bad, as I said. Okay, so where we are with what are we learning a little bit? So we seeded these black holes. Thanks for that question. It was clear early on in the simulation. The black holes in the simulations have merged and so on, and maybe some have evolved in isolation. They're still in the outskirts of satellites moving around. And what we end up seeing is that the number of black holes, right, is are wandering black holes, the number of intermediate mass black holes scales very clearly with the mass of the galaxy, right? So this is the mass of the galaxy on the x-axis. It's very easy to see, obviously, that we find more and more in larger galaxies, right? That are related. So small galaxies may have a few wandering black holes. Large galaxies will have hundreds of these wandering black holes, hundreds of these intermediate mass black holes. But most, and that's what this blue line represent, the number that is actually accreting enough to be an hyperluminous X-ray sources. Most of them aren't, right? There's a factor of 10 between the total number and the ones that actually can be seen. And maybe it's more frequently in the smaller galaxies that we can see them. So I said it's okay that maybe we don't see them because maybe their mass, it really has been retained as their seed mass. So how are we going to see them? Well, there's a lot of excitement because we have a way of measuring their mass. There's a new gravitational wave instrument that is going to be launched from space, LISA. It will launch in the 2030. And what it will see is basically this intermediate mass black hole population. So if these black holes are there, now we finally get a very precise measurement of their mass. And when we measure these intermediate mass black holes, what we're learning from the simulation is that it's likely a very, very good proxy of what the seed formation mass was. So what we're seeing here is the distance in terms of redshift. So we're going to earlier in the universe, even a very, very high universe. And this is the total mass of the source that LISA will measure with various signal to noise. So this big peak here says that LISA is going to see mostly merges between 10 to the 3 to 10 to the 6, exactly in the range of where this massive seed formation in intermediate mass black hole should be, right? So most of the detections are going to come, in fact, from these and maybe some of the more massive ones, but and so we have a really good chance. This is going to be like precision gravitational wave astronomy, where we get all the intermediate mass black hole merges, possibly all the seed merges, and a measurement of the mass through their for the ones that are merging.
You can't LIGO measure?
Sorry?
Why can't LIGO measure?
Because of the frequency that it works at. So I'll show you in a second, right? So we have a strain amplitude, a gravitational wave amplitude that scales its frequency, right? And that frequency scales as the mass of your source, right? And so you need to go to low enough frequency to see the big black holes. That's how the scaling goes. So LIGO can see up to sort of 100, right? We've known about but after that, it's not in the frequency range that we'll see this. This experiment from space is going to have these sort of giant arms, right? They are like 1,000,000 kilometers long, and it's going to be sort of like a tripod thing going around the Earth, right? And
that's why you have to go to space.
yes, indeed, right? You have to build this huge interferometer, and yes, exactly right. So that's what it's made for, to catch the massive black hole population, right? Not the galaxy one, the ones that are there. So we're really excited about that. And when we look at the simulations, we say, okay, what kind of black holes are undergoing mergers in the simulations? To the best that we know, I told you these sort of nested simulations to try and resolve this this black hole mergers. So this is just a simple histogram of the mass of one black hole versus the other, M1 versus M2. And this color region here indicates in red where most of the events are. There are indeed, most of the black hole mergers are predicted to be indeed in this very small mass range, and to be indeed seed black holes that actually undergoing mergers like we saw in that movie, right? That is sort of also reproduced here. This is just in these blue crosses sort of indicate where most of these events are, sort of, and here we're zooming in sort of to these 3 samples, for example, right? So these are actually dwarf satellites moving around large galaxies like the Milky Way as its satellites. These satellites themselves have undergone some small mergers. There's a lot of these events are coming from binary black holes that eventually collide in this in the outskirts of large massive galaxies. This is sort of a representative sample of the objects that fall into there that we see in the simulations. So they are there.
So Tiziana,
Yeah.
I'm looking at the color scale. So 10 to the 4 is your dark red, right?
Yes.
So How
is
many events are we talking about? 1 million events?
close, yeah.
Over what? This is over a period of 10 years? Or is this
Oh,
per
right, yeah,
year?
so this is just all the events in the simulation, so it's not Lisa.
Oh, you haven't put Lisa sensitivity.
Correct, yeah, so
Okay.
this is everything that merges in the simulation, so you're right, over the lifetime of Lisa, or 4 to 10 years, whatever we want to call it,
Yeah.
there will not be many,
Okay.
but there'll be tens, yeah.
Tens,
Yeah,
okay.
yes, so this is just the magic in the
Everybody.
simulation, in the universe,
Yeah.
right? Yeah, but not what can be detected directly. So again, here is how we want to sort of go back to also what does the signal look like, but again, not convolved with a lifetime of Lisa, right? Although here it says Lisa 5, yeah, just in the sensitivity. So the way we look at these events, right, they span through a frequency, right? So the black holes are coming closer together, right? And they move through this plane this way, and then eventually they merge. So the gravitational wave, they disappear from the universe, at least in gravitational wave emission, right? Or it's all radiated off. So this is sort of how they follow through. This is the sensitivity curve of Lisa. So anything above this black line is detectable by Lisa, and this black holes follow. They go smack on into the main sensitivity area of the Lisa, right? So the frequency range is seen here. This is just the amplitude, the strain amplitude that we have. Again, I'm plotting all of the events of the simulations. This is how they will look like. All these orange ones are in fact seed black holes. So the majority of the events, if Lisa switches on, are possibly, maybe, seed black hole mergers, or the few events that they will see, and these are events that, actually these mergers take a while. They're not necessarily a very high redshift. By the time they start merging, they're going to be a redshift 2 to 3, so roughly half the age of the universe rather than very early on. So just a few, a couple of other things. So these are other mergers, right? So some of these black holes go around supermassive black holes, so we see them in there as well. Some of these will be called by Lisa, so these high, some of these measures are intermediate mass ratio in spirals. These are very interesting, and we have them also in the simulation. There's some places where this seed black holes is going around a very massive black hole, right? Or maybe there's a population of them with some of these mergers. So extreme radio mass in spirals from a 10 to the 10 black hole, and a seed black hole that merges into it. These are really cool events. We'd like to know about them. Maybe they're not quite observable by Lisa. They're a bit too low frequencies, but they represent unique ways for us to probe gravity, because they will orbit the black holes for a very long time, and there'll be really fun events that we want to know about. And all of this is, things that we're getting a glance at in the simulation. So talking of very massive black holes, maybe I'll just say a couple of things about other things that happen in the simulations, the formation of the most massive black holes. This is another example that Ying looked at. So that this is an episode in which they see the formation of the most massive black hole, sort of at cosmic noon, right, when lots of the quasars are on, there's lots of mergers and so on. And here we are seeing a triple mergers. These are very, very massive galaxies already in the simulation. So these are rare events as opposed to the more common ones. And we see that there are 3 galaxies that come in. So the three, it will start again. We have these 3 crosses, these 3 black holes, initially 2. This gets close to this central one. This other one comes in. There's this one starts merging with this, and eventually the third one also merges. So there's in this simulation, we catch rare events, 2 successive galaxies of two successive mergers of 2 massive galaxies with massive black holes that are coming in and form objects that are the absolutely most massive black holes in our universe, approaching 10 to the 10 solar masses, 10 billion. So a precursor of this kind of event, when these objects are just coming in, it's the formation of what we call a triple quasar system. Some of these have been observed, so they're exciting systems, right? And another thing that we can look at is where would they see, as I said, there are some of the most massive black holes. If these are all the black holes in blue here, the simulation, their masses as a function of the mass of their galaxy. This black hole, after it merges these three, ends up very high up in black hole mass and stellar mass. These are the most massive black holes in the most massive galaxies. Things like M87, right? That they would end up in some of the central cluster galaxies today, maybe even more extreme than that. So yeah, in fact, in this simple distribution, we are plotting the black hole mass, right, of just counting black hole, the black hole mass, and we are just coloring these two distribution in different colors, where this greenish one represents all of the black holes in this extreme mass range, the most massive that we may have. We've seen that most of them would have gone through a triple event, a major triple merger, in order to form the absolutely most massive ones in the universe that we have. Maybe M87 is more on this side of things, right?
You're going 10 times larger mass.
Yes,
Wow.
yeah. So if we're looking for the big monsters, maybe they would have gone through one of these phases.
I'm one of those.
Yeah, come on. We have to. So, but black holes don't only merge, right? We have this complex dynamics, complex systems within the resolution that we have. So we may have merging, but some of these systems are chaotic, are messy, there's complex dynamics. Some of them will just stall, black holes will just move around each other. And we see some of them that get kicked out as well, right? This is, again, in these sort of chaotic dynamical systems that can also happen. And it's kind of fun that we see some of these events. So again, there's three black holes in here, the galaxies come in, these three black holes kind of get coupled together, but then this shoots out. So there's, in this complex dynamics, we also see that. This is I'm mentioning because also Priya and people at Yale have claimed that maybe there is a signature of a black hole. This is an observation, right? Where they've seen this stream of star formation close to galaxies, and they claim that this could be one of these black holes that is running away, that's being sort of kicked out of galaxies. In our simulation, we actually see that it's more common when you have these streams, and again, I promise it's maybe the last movie. When we get this stream, it's more likely to be a flyby encounter of two galaxies. So the galaxies kind of skirt each other and pull out, sort of the tidal tail, a lot of the stars. So maybe this is now the most significant telltale signs of a black hole being running away from a galaxy, but the jury is still out for sure. And it's really interesting that we are perhaps also probing this observationally, and be great to get some limits. So I'll really wrap up. I'm already out of time.
That's okay, we started a little late.
You're okay? Okay, I'll probably. So I want to just mention one little thing and I'll really wrap up. So I'm going to now zoom in a little bit into this epoch of the first quasars, right? That's something that we studied a lot with these very large volume simulations. We're looking for rare objects that grow very fast and see if those are consistent with the way we form black holes and galaxies. And we did a lot of work over the years, and other teams as well, on these first quasars. The bottom line is that structure formation can occur really, really fast in some location, even in the early universe. Sort of speeds up the growth of black holes. In rare places, it can really do that, and it's not too hard. And I think it's consistent across our models that we see that different conditions can enhance the growth of black holes in some places in this universe. Okay, so what I'm showing here is from the simulation, all these lines again, the number of black holes per unit volume. So the number density of black holes as a function of black hole mass. So this is a black hole mass function. And so we see black holes at small masses. So there's a lot of these, right? This is still very early universe, right? It sort of hits the quasar, the first quasar, redshift 6, the billion-year-old universe around the middle of these lines. So what we concentrated on, we did this huge giant to see, are there some big ones that form early on? The answer has been yes, right? But we also, because black holes were seeded according to any stars that starts having some kind of gas that cools and so on, sort of inspired by the way black holes should form, there were a lot of other black holes besides this monster iceberg, tip of the iceberg, huge monster that we could catch in these large volume simulations. And those are the ones that eventually stay around, right, and make it into galaxies, some of the seeds. But even at this high redshift, there's quite a population of black holes here, right? Seen in another way, this is just a luminosity function of the same population of black holes. This is in X-ray. This bars here are some constraints on what the luminosity function was like. So the quasar observed are the very, very bright ones, right, that sit at the bright end of this, and they're very rare, right? So there are very few of these objects in here. And these are the simulations here. And again, we still had a lot of these other black holes that are part of the way that we see that, you know, after being seeded black holes, a few of them very rarely grow enormously. Lots of them grow a bit, right? So where I'm going with this is that I'm very excited that now with JWST, I don't know if you've heard about this, the little red dots, or you tell me they also called the monster something. Well,
Hidden little monster.
the hidden little monsters. So one of the surprising and exciting discoveries from JWST, looking at the same epoch, this early universe, was finding this what has been attributed to being sort of million-sized solar mass black holes, massive but not extreme, in a lot of galaxies, right? So these are not the rare first quasars. These are like common, relatively common galaxies at this epoch. And this is the observation from JWST, just one subset of it. And they're called red dots for obvious reason. And there we are. And in the simulation, we always have those. And we're trying to hide them, not hide them, but we're like, oh, maybe our models is wrong because we have so many extra black holes in there, right? So to me, it's personally super exciting that, you know, things are sort of coming together. Sure, there's a lot of non-resolved stuff in the back. We are capturing perhaps also the population of this black holes that should be there if we kind of grasp enough. We have the way that black holes are seeded, the way they're growing across the full mass function of galaxies, right? With some extreme ones, but lots of other ones as well. So these are some images we made like before, right? That what would the galaxies look like and what the AGN, and they're really, really red in the simulation. So you can use the simulation to make mock observations and let's see, maybe with Fabio, we're going to revisit properly. He will say, oh, I'll be interested, and we can try and see if they really stand for us as a way to understand also this new discovery by JWST. So I'm happy. Okay, so that we're finding the largest population of black holes, really not just this tip of the iceberg early on, and this only puts more sort of visibility. So I really should shut up now. I've talked enough. So I tried to take you a little bit on a journey, picking a few things of this black hole universe that we simulate in this large cosmological simulation, sort of nested in resolution to try and grasp as much physics as you can, but keeping this idea that these black holes are merging with the rest of all the structures in the universe. And this reminds us again a little bit of the problem of, you know, wanting to understand, reconcile the largest structure of our universe with some of the smaller structures in many ways, and propel us forward in trying to unite this view that is the most challenging view about these objects, right? How they can link to gravity at the larger scales and the smaller scales. So I'll stop at that and yeah, take any questions.
Thank you, Tiziana. Questions?
It's great to see you.
Yeah.
Excellent. Do you track the angular momentum of the black hole particles in this simulation?
Oh, you're asking the hard questions. Yes and no, to some extent, not when they're very close though. Yeah, we don't have a very good way of tracking that. Yeah. So you can a little bit, yeah, to some extent when you're, it depends what scales you're and how well you want to know it. Obviously there is angular momentum, you see these orbits and all of that, right? So, but it depends. Are you asking very, very close to the?
No, but like, just in general.
In general,
yeah.
Yes, yeah, to the.
But so like for the most massive, let's say, black hole particles,
Yeah.
you have like an estimate of the accumulated, let's say, angular momentum or?
But you mean in terms of associating a spin to the black hole, or?
Yeah, I get that would be more difficult to do, but just the angular
Right.
momentum was a
Yeah, so we
that-
haven't,
you know.
so we have it because obviously you see these orbits have their, these black holes are moving in these orbits, they're moving, so we can definitely measure. And depending what, so as a proxy of,
Mhm.
maybe trying to understand maybe what the spin. Some people have actually put in, based on exactly what you're saying, tracking a little bit the angular momentum around this particle, the massive ones, they're trying to capture and in this coarse representation, give a spin to the black hole population in this topological simulation. Yeah. So there is some coarse tracking. Yeah. Mhm.
So you described this prediction that the biggest black holes are, triples and
Perhaps.
mergers. Yeah.
Yeah.
Yeah. Are those good targets for pulsar timing arrays, or are they outside
Yeah, right.
the band? Or
No, I actually have something on, I think I've written my slide about it. I'm actually quite excited because, so if we have some good, this would be things that you would see almost in the next few years as single events, but even would be the ones that dominate the pulsar timer array. Definitely these would be, there's this very, very loud massive mergers that would definitely dominate the signal in the pulsar time. Even the background signal, the component from the black hole mergers would be dominated by these type of events.
Okay.
Yeah.
Thanks.
Well, last question actually. So in your simulations, in the little red dots, why are they red?
Oh, because Yayin can tell you all about them. No, because they're and they're obscured.
Besides dust.
And there's a lot of, so there's a lot of gas. Galaxies are forming really, really fast. There's a lot of star formation in these little galaxies, but also that contributes to the obscuration to the quasar predominantly. So there's there's still quite a lot of dust. There's just so much star forming gas that it's really hard to not redden them. Yeah.
Okay.
The colors in the simulation meant to be like physical colors.
Like when you see the movies and things like that.
Yeah. Like, does it predict that those things are red?
I mean, you have, so you have, star formation rates, metallicities, the age of stars are properties that you have. So you can turn that into a prediction for, and the spectral energy distribution for the stars or the AGN, and with the dust more, sort of mock as a real color. Yeah. So there's that enough information to have ideal colors. Yeah.
All right, let's thank Tiziana again.